All right, guys. I hope you had a good break and good lunch. It's a long day. Let's get back to the 7-second display first to talk about the details of the LEDs. Then we'll move to the lab, right? It's a heavy load alert for this week. Be careful. Just don't wait until the very last day to start working on the homework, right? If you scroll down, you can see there are 10 tasks, even though some of them are pretty simple, but still 10 tasks, 10 points for each. Okay, so let's get back to the improved home alarm system first, right? So what's going to happen is we are going to use one of the 7-segment display modules. So you have how many display units on the board? 4, right? So we're only using the LSB, the rightmost one, to indicate that if the alarm is on or not. So it's going to display letter A or 0, number 0, which is just all the LEDs, a circle LED, to indicate that it's so 0 is off. A indicates that the alarm is on. Okay. So in that case, we need a decoder to know which one we want to turn on in the LEDs. So this is a Verilog code for the decoder. You are going to use this a lot this term. Now let's take a look at it. So it's taking an input. So it's decoding the number input into actually the signal for the 7-segment display. So if you want to turn on, so in the morning we're talking about the 7-segment display circuit. There are LEDs with anode and cathode. If you want to turn on one individual LED, do you need to give a 0 or 1 to turn it on? Just to remember that? 0, right? Because it's connected to the cathode. So it's connected to the cathode, and all the anodes are shorted together. See? All the anodes are shorted together. So there are individual LEDs, and you short all the anodes together. And why that still works? Why do you think that makes sense? So see, all the anodes, right? The anodes of the individual LEDs are shorted to one node. You're not splitting all these wires, just one voltage node. But for the cathodes, you have different ones. Okay. Yeah, that works because you just need a 1 voltage power supply at the anode, and you just keep, if you give a 0 to E, for example, then you are running current through the LED E. Okay, if you give a 0 to LED D, you are running current through LED D. So you can still control individual LEDs by doing that. So it's okay to short all the anodes to one node. Okay, and this type of connection is called common anode connection for this 7-segment display module, and some of them are common cathode. So it's just the opposite way. You have all the cathodes shorted together, and then shorted to where? If you have common cathode, so this is common anode. You can see all the anodes are being shorted together, so it's called common anode. Okay, so if you have a common cathode, which is a different type of display module, so you have all the cathodes being shorted to one node, and then shorted to where? Ground. Okay, and then you want to connect your individual anode to the power supply, right, to the voltage. Okay, if you give a 1, you're turning on the LED. Okay, that's how that works. So let's go back to the Verilog that controls the 7-segment display over here. Okay, I think that's this guy. It's taking in an input which is 4-bit in order to show or select the entry here in the switch statement to find out which one should be delivered to SAG. So SAG is a keyword. It's like an LED and switch, SW, the keyword for the IPGA, because it's the physical component on the board. And the SAG is a 0 to 7, so it's 0 to 7 is 8 bits in there. So each one controls one LED for each unit. Each LEDs of the segments and also the dot over there. But we're only using, if you count how many bits we have over here, you can tell it's 7, right? If you count, it's also 7 bits. So we are not using the DP, the point. So all these bits are controlling the bar LEDs only. Okay, make sure you know what's happening here. And if you look at the constraint file, oh geez, I don't have the constraint file, but I'm going to show you later. Because the constraint file uses SAG. So SEG, SAG is a keyword. So only use 0 to 6. So 0 to 6 has 7 bits. It controls A to G. So all the bar LEDs on the display unit, but no DP. Okay. So you can see these are the code that turn on the certain LED or LEDs to display a number or letter in a common area. So the first one definitely display a 0. So if you want to display a 0, you want to turn on which one, turn off which one for the unit. Turn off the middle one, right? And turn on all the rest. So it's going to be a 0 or O. There's no difference. 0 and O, couldn't tell the difference. So in that case, if you look at the code here, okay, remember 0 will turn it on. So 0 will turn it on, okay? 1 will turn it off. So do you think 1, the MSB over here controls which LED? The middle LED, okay? So what's the letter of the middle, what's the name of the middle LED? Label or name? A or G? I'm not saying the display, I'm saying the name of it. But let me open up another one. So I can open up 2 web pages at the same time. Okay? So the middle one is what? G, okay? So in that case, if I list my combination of code like this, the 7 prime B, 1 and all zeros, is that from G to A or A to G? It's G to A, right? Okay. So I'm using all zeros as an entry, as a, how to say that, as a number to enter that entry. Okay, can I use a different number there? For example, can I change this one to 1, like 0001, to enter that entry to display a 0 here? You know what I mean? Does it matter for this number here? So what's the goal? The goal is to display a 0 there, right? Just turn on certain LEDs. It just depends on the key. So the first number over here is like a key, okay? You can use like 0000 as a key to turn on that 0, or you can use whatever you want to use, like for the 4-bit combination. Can we use 5 bits? A 5-bit binary number. Yeah. 6 bits. 3 bits. What's the problem of using 3 bits? Yeah, so 3 bits will give you how many options? 3 bits will be 8, right? So how many different characters you want to display over there? It's definitely more than 8. It's 0 to 8. 0 to 9 is right at 10, and then including all the letters. And you can display other things as well. So, the number of bits you want to use as a key depends on how many options you want to display on the unit. Make sense? Right? Cool. I'm using 0 to represent 0 because it's just more straightforward. You can use any other numbers as a key, okay? So that's a decoder for the 7-segment display, okay? So as a decoder, it has an input. It takes in the input and output a code for the display module. So it has just 2 directions, input and output. So input will be the key and output will be the code for the display. pretty straightforward. So if you want to use it for the home alarm system, or the little example on the FPGA board, what can be used as the input, you think? So what is the utility on the board can be used as the input? Switches. So you input the switches, 4 bits or switches, you give a like 1 0 0 0. You're hoping you can display an 8 over there. Okay. So this is the top module directly interface with the FPGA. So switches will be, I'm putting five switches over there. Doesn't matter really. And LEDs, only 1 bit of LED. For the home alarm system, I think it's a very similar example from the last one, but getting improved. So the LED, the LSB of the LED is being used as alarm. So whenever the alarm is being triggered, LED will be on. So I just need a 1 bit of LED. And the 7-segment display module, that unit, is just showing you that if the alarm is on or not. So it's just displaying a letter on that. If the alarm is on, you put an A on it. If the alarm is off, you put a 0 on it. So it's not signaling an alarm. It's just a power indication for that, indicator for that. And SAG, is a keyword because the top module is the keyword for the FPGA. It's a direct interface with the hot wire. The wire, the traces connects to the unit. And AN, I didn't talk about it in the morning, but let's take a look at it. So AN is a keyword. It controls which unit of the 4 units you want to turn on. Should be turned on, okay? So AN has, I can tell how many bits do you have for AN. How many bits do you have for AN? How many bits do you have for SAG? SAG, SEG, the keyword SAG. I just talked about that, but see if you guys can remember it. How many bits do you have for SAG? Let's take a look at it. All right, that's the constraint file. You can find out the connections between hardware, the pins of the FPGA, to the whatever keyword you should use for the top module. So these are the names of the top module you want to put into your top module, the Verilog, right? So these are the SAGs. How many bits do you have for SAG? 7 or 8 or 8. Yeah, 0 to 6, that's 7 bits for the bars, but you got 1 more bit for the point. Okay, so for SAGs, you actually have, yeah, right, actually. So SAGs have 7, but DP is the actual one, has a different name. So it's not SAG anymore, it's just DP, right? So could you tell if SAG 0, the LSB is shorted to which pin here? Right, take a look at it. Just look at this one. So shorted to, so CA, so A is shorted to W7, right? Okay. And then you look at the constraint file. W7, pin W7 is shorted to where? SAG 0. So 0 is shorted to where? To which LED? So SAG 0, right? SAG 0 is shorted to W7. And W7 is shorted to A, LED A. So SAG 0 is shorted to which LED? You know what I mean? So W7 is over here, right? You got SAG 0 shorted to W7. I have LED A shorted to W7. So SAG 0 is shorted to which LED? A. Okay. And no, just a moment ago, it just told me here, here is G2A or A to G? G2A, okay. So does that make sense? This one is gonna be A, why this is A? Why the LSB here is A? Because it's sag what? It's sag 0. Does that make sense? Okay. And for AN, like what I said, ANs are shorted to W4, V4, U4, and U2. There are different paragraphs in the constraint file. You can find them over there, similar to the sags. And like what I said in the morning, you do need zeros for these and for these to turn on the LED. So the two conditions need to be met at the same time. So you need a AN to be 0 and the certain LEDs cancel to be 0 and will turn on that LED. So the ANs are the enabling pins to enable each individual LED unit, the display unit, because it's on you can see it's on the top, right? So it's like a switch on the top. It's dumping currents to the entire unit. So if you want to, for example, you want to turn on only this guy, for AN320, what is a 4-bit code do you need to only turn on the rightmost one? So only turn on the rightmost one. For AN, what's the code for AN? To only turn on this guy. So AN is the 4-bit number, right? The
111.
That's right, yeah. You agree with that? You all? Yeah, because you need a 0 to turn it on, right? So just keep AN 0 to be 0, but all the other ones are 1s. So you can only turn on the LSB unit. Cool. So you know what is AN, okay? You know what is SAG, what is LED, what is switch. It's all clear right now. It's the top module direct interface with IPGA hardware. So what do we need? So we need this decoder. So decoder is just a decoder. It's taking in input, like a 0 to whatever, 7, I think. It doesn't matter. So all the 4-bit inputs, and it's going to output a 7 displays code to turn on certain LEDs. It's just decoder, but nothing else. And the top module is a interface to the IPGA and taking in all the sub modules. So I have 2 modules right now. So what else do you need for the home alarm system? What else do you still need? So I have a decoder. The decoder is going to show an A or 0 at the LSB of the unit, right? So indicate that if the alarm is on or not. And the top module is building an interface. Let me show you. This is a decoder. 4 bits input and output a SAG, which is 620, 7 bits. And now you have a top module, which is IPGA interface. So here is your 7-segment display units. You got 4 of them, right? So the SAG, they directly connects to the whatever interface with the hardware on the board. Okay, and you need ANs. ANs are, the control bits. It's from 3 to 0 here. Connect to the ANs. So what else do you need to make it happen? It's a home alarm system. So you are expecting using switches. using switches to trigger that alarm of the LED here. You got LED 0 to 0 is just one LED, right? So what is feeding the input to the decoder? Yeah, switches. How many do you need? So you can assign different numbers to it, but let's just assume we need a 4, okay? Yeah. So these will be the inputs feeding to the decoder. But is that an alarm system? So just, you got coffee leaking there. Is this a home alarm system at all? Like you are using switches to this number of switches. Let's take a look at it. So you got to use the home alarm system. You know, we used. I'm gonna open up another one just in case. We covered it here. Is that this one, right? So M is a switch that you are switching on and off that alarm system. And the 4 here is a trigger, a signal, okay? And that's the output. So this output should be connected to the L is a single LED, okay? So you do need another, you need another module here. Okay, have a output, that signal, and have as 3, as 2, as 1, as 0, and you have M. So because M is a switch, you want to switch on and off that alarming system. So I think you can definitely use one of the switches to do that. It's not a problem. Let's just use one of the switches. I don't know which switch it is. It's just one of them, okay? Just directly connect to it. Okay, it's easy, right? Easy to do. You just include this module into your top and then use the dot something, parenthesis something to make the connection. No problem on that. So what about these ones? Let's see what we do here. So for S, let's look at this one, okay? So 4 of the switches are being connected to S. Since we have 4 signal lines in for S, okay? So switches are actually connected to the switches this way, but not directly connected to the decoder, right? So it's like this. And that's 4 and connect to here. So I think the main part is over here. Whenever the combination is SW is a switch 4, which is the enabling pin, you have to turn it on first. And the other 2 are zeros. you are where this came from? Like what I said, so the output over here is being shorted if you look at ACT, right? So the ACT is the input for the 77 display decoder, if you look at here. So the 4-bit input to give you a corresponding output. So it's actually in the lookup table here. If you look at 0, the input is 0, 0, 0, 0. If you want to give an A, the input need to be 1, 0, 1, 0. So it seems like only the bit 3 and bit 1 are being toggled in order to show a difference on the display module. It's a weird way to do it, but that's how it was done here. Could you tell? So if you want to display a 0, you need 4 zeros. If you want to display A, you need 1, 0, 1, 0. So in that case, you can use one switch. If you switch that on, you're giving a 1 to bit 3 and a bit 1 at the same time. Because these two are constants. So you're giving, if you switch it on, you're giving a 1, 0, 1, 0, which is going to show A on it, because this is the input of the, that's the input of the, for these guys. So what's happening is there are 4 wires being created. 1, 2, 3, 4. It's called ACT. So these wires are shorted to the switches, and then shorted to the input of the decoder. Actually, this exists in the design. It is boring, I know, but it does exist, because you can see ACT here is being directly shorted to. Okay, so this is something new here. Okay, so usually when we make connections in the top module, we have a dot something in parentheses something, but this guy doesn't have it. Pay attention to this, okay? It can be confusing. What's happening here? So in the top module, you include a sub module, right? Then you make the connection with the dot something, parentheses something. But this one doesn't have any of the dots, which is okay. So it's just trying to make it simple. It's the same way to make the connections from these signal lines to the signal lines inside the module, but I have to follow the certain order. So if you look at this one, look at that one. So ACT is being claimed where? In which module? ACT is being claimed in which module? In the top module or in the sub module? So ACT is being claimed here, right? So it's exactly in the top module. So which means if you don't have a dot something parentheses something, you can also directly just write the top module signal in the same order as signal lines in this sub module. Is going to directly make the connection automatically. So ACT is the first one you place in the parentheses, right? So if you go back to the decoders module, what is being put in the first? The input, right? So the input is being shorted to ACT. That's just a different format to program it. So input in 1 is being shorted to ACT in the top, and output here, output 1 is being shorted to SAG, and then connected to the hardware of the IPGA. Okay, so the next problem is very similar, but I think there's one thing you need to be aware of, which is, yeah, nothing. It's just a straightforward. I think this is easy to do. Okay, now let's get into the lab. Okay, so the lab is the 2-week lab. I prefer that you put the two reports in one, but the week 1's report is due next week. Okay, you are not finished the 2 labs 2 weeks from now. It's you got to finish one by one. I don't want you guys to push.
2 separate reports.
2 separate. It could be 1 report. It just keep adding to it. You know what I mean?
Oh, okay.
Yeah.
So upload it and then come back, edit it,
Yeah.
upload it again.
Yeah. Yeah. So the first task, okay, is several combinational logic blocks. I think there are 2 of them are pretty interesting. It's not really super basic, but not too difficult as well. So the first one is a 2-bit adder, 2-bit full adder. So if you look at the structure of it, 2-bit full adder has to be 2 FA modules. Okay, so the better way to do that is create an individual FA module, okay, and reuse it. You know how to reuse one module for several times in your top module? You just declare or include it twice and rename it UT1, UT2. So you create FA as one module, sub-module here. And within FA, you know the logic, right? So you can have, for here, one quick quiz question here is how many inputs and how many outputs for the FA full adder? One single 1-bit full adder. How many inputs, how many outputs? 3 inputs and 2 outputs, okay? So you can have FA module input ABCI, output SCO, and parentheses. Okay, you have signal lines as assign S to be A, XOR B, XOR CI, and CL will be, we just put it on the paper this morning. I think it is A, B, right? A and B, sorry, A and B, or what? A or B, right? A or B and CI. Okay, so to here. Okay, so that's the logic. Yeah, that's it for FA, I think. Then you can have a top module, and in the top module you you could have another one, right? You can call it FA 2-bit. So you are just having 2 FAs in one bigger module here. You call it FA 2-bit. So in FA 2-bit module, you include FA twice, and each time you rename it. Okay, and for the middle wire here, for the middle connection here, because every FA has a CI has a CL, right? So for the middle wire, when you're making the connections, for the first FA, UUT1, you have .co, which is a CO here, connect to the wire. So it's like a piece of floating wire over here. So the CO here connect to it, and the CI of this guy connect to as well. So they are indirectly connected to each other by that little wire, floating wire in the middle. Does that make sense? You know what I mean? Because for the 2-bit full adder, you need the 2 FAs. You need the 2 1-bit FAs. Okay, and this is one. This is another one, and it's going to be, since there are 2 bits, you're adding 2 bits binary numbers. It's A0 B0 plus A1 B1. And you have to consider CI as well. CI is somewhere else. You have to consider CI as well. So CI comes in at the same time. And C out of the first one will be the C in of the next one. Okay? The carry out of the first one will be the carry in of the first one, of the next one. Because if you if you have the two-bit binary numbers to be added together, like 1, 0, and 0, 1, for example, you're adding these two together, 1, 1 plus 0, 1, okay? So this will be the C out, the carry out of the first phase output, right? And 1 plus 1, you're getting a final C out. So this one will be, this carry out will be this. Is that correct? And this carry will be this. So this being used for here, for the addition over here. So that's why you have to input the C out, the carry out of the first one to the second one. Mm-hmm. No, because you're adding, yeah, that's right. Yeah, you're right. A1, that's B1, B0.
The carry out from the
Yeah.
B's would go to the A's.
Yes, that's right. Because you are doing A0, B0 plus A1, B1. You're adding B's and ones, B's and A's, right? Yeah, thanks. Good catch. So you can create another the FA 2-bit to include the two as the FA twice and make the connections to form a FA 2-bit. And you can add another top module to include switching the LEDs to to this slider. So the final output could be connect to the LEDs. You can use the LEDs only the 3 bits, I think. 1, 2, 3 bits of the LEDs to display the result, final result. Okay, that's a slider, and there's a multiplexer, but using the conditional. I don't know what's the name of it. Have you used this somewhere else, like in C++ or not C++? Python or no? No. So it's like is y equals S1? If yes, you select the first statement. Okay. And then you make checking this again. If S0 equals D3, then you select. Wait, no. How that works? So if S is 1, it selects the first statement, okay? And if 1 or 0, select the first one, do you remember? So it's like, what's happening is, it's an assignment operator here, so the equal sign is assignment operator. It's trying to assign one of the inputs from D0 to D3, there's 4 inputs, it's a 4 to 1 mux. It's a multiplexer. So if I believe if S is 1, it's either 1 or 0. Let's just assume it's 1. So if S1 is 1, you are selecting the first statement, okay? It's being separated by a column here, so you are selecting the first one, all right? And if S0 is 1, you are selecting D3. So eventually, if S1 is 1, S0 is 1, you are selecting D3 as a data to be sent to Y. All right. So what about S1, S0 to be 0, 1? Which one is being sent to the output? S1, S0 to be 0, 1. So it's like if it's a question mark over there, right? Okay. So if S1 1 or 0, if it's 1, it's selecting the first one, okay? And then checking S0. If S0 is 1, it's selecting D3. So it turns out to be 1, 1 to be D3. 11-2B-D3. So that's the multiplexer. You have 2 bits to select one from the 4 digital inputs, like D0, D1, D2, D3, right? So if you have S1, S0 to be 0, 1, which one is being selected? D1, yeah. What about 1, 0? D2, 0, 0. D0, right? Yeah. That's how to use that. So you can build a multiplexer easily, just a one-liner. And it's, I don't know, maybe 5 to 10 gates and like 30 transistors will be synthesized on the IPGA. It's just super convenient. It's way better than LT Spice. Okay. And we are also doing a running LED. If you look at it, it's cycling or rolling one LED from one end to the other, and the frequency is 1 second. So there's a thing that you can control the frequency of it. It's called clock. So there's a onboard clock. It's 100 megahertz. Because you know it's 100 megahertz, so there are 100 mega cycles 1 second. So you can use that one as a reference to create a 1 second thing. So what happens is you count it, you set up a parameter. So what I name it here is count CNT max. It's a maximum count I want to use. It's a parameter, it's a constant. So whenever the count reaches that count max, I'm going to do something. And then set it to 0. So every time it's being set to 0, it's ready 100 mega clock cycles, which is 1 second. So in the constraint file, make sure the clock section is being uncommented in order to run the clock.
And so you can't just change the frequency by changing the period in the constraint file?
No, the clock is the hardware is already physically on it. You cannot change the frequency. But you can divide the frequency. So that's the highest frequency you can have, right? 100 megahertz. It's still pretty fast, way faster than the Arduino's, which is, 16 megahertz, right? So this is about like 6 times faster than that. And also you can divide it, for example, when clock count by twice, then you reset, then you toggle a signal in order to divide the clock. So you can actually generate any kind of frequency based on that 100 megahertz by dividing that clock frequency. And we're going to do some clock division later on. But this time, I think it's just a counting. So you can see this is a decimal number. I have 32 binary bits in order to handle that 100 mega, that number here. It's a decimal number, which is 100 mega. It's just 100 million. It's actually not 100 mega. It's very close to it. What's the difference from million and mega? Mega is 1024 times 1024. Million is just 1 million. So 1 kilo in computer is 1024, right? In general. So this is not exactly 1 mega, but it's very close. Super fast, nobody can tell. But if you are creating a very precise digital clock, you probably want to use 1024 times 1024 instead of 10 million, 100 million. So 100 million is what? 1 million is 1024 times 1024. So 100 is going to be 100 times that. Okay, so you set up a parameter which is a constant, and you are trying to reach that constant, then do something. Okay. Also, this is a new thing to let you guys know. So in the sensitivity list, I have not just a clock. So CLK is a keyword. You don't use CLK for some other purposes. So CLK is a keyword, represents a 100 megahertz clock on the board, and RST is a signal line you created in here. It's eventually being shorted to a switch. So whenever the switch is on, you just reset everything. It's going to restart from our beginning state. It's just the one additional option. So sometimes the digital system can run to wherever. Sometimes nobody knows, just because of some of the errors. So you do need a reset function on the board, hardware. You can just reset it. So it's going to come back to the very initial state. So usually we'll add a reset switch. So I'm going to use a reset here, which is a nag edge. So for clock, it's detecting the pause edge of the clock. It's 100 megahertz, is always cycling. So it's detecting the pause edge, the rising edge of the clock, in order to update the whatever in the always statement. There's a huge benefit of using that always statement with a positive edge triggering mechanism using a clock. You are thinking like, why do we have to waiting for the clock to do something? What's the reason for that? You can synchronize things. You can always keep things updated, and it doesn't matter because it's super fast. Nobody cares. You are thinking like, wait, who is waiting? It's the fastest thing probably in the lab or in the building, so nobody cares. It's going to update things really quickly. So anything changes, it is able to have a response inside the statement very quickly because it's always detecting that signal change in the sensitive list. Okay, so we got a rising edge. It's always updating things in here. It's always detecting the falling edge of the reset as well. So whenever reset getting a negative edge, is dropping from 1 to 0, it's going to reset everything. Just move the LED to the initial state. So you can see whenever reset is 1, I think there's a bug here. It doesn't really matter because I think it's because of the bouncing back and forth. So I'll let you guys try pause edge as well because I'm trying to use if reset, which means if RST is true, right, with 1, it's doing these things. It's actually a rising edge, but it worked. So I think initially from the one of the instructions is probably there's a typo. I think you can try to use either RST equals 0 or equals 1 in order to trigger it. It's because when you are doing the switch, I think it bounces back and forth for several times. It doesn't matter it's on rising edge or falling edge. There's always a edge over there. So it's detecting that and doing the updates. I don't think that really matters. So for the if statements, it's very similar to C++. You got an if and a bunch of else if and eventually else. That's the basic structure of it. So if, else if, else if, else if, else. That makes sense? Or if you only have one condition, it's going to be if, else. Just 2 conditions. Something or something else. Okay? So if it's being reset, then reset it. So LED, you are giving the very rightmost LED to a 0, you turn it on, but all the rest are zeros. You turn off the other ones as an initial state. So what's the count should be? If we reset it, the count should be what? 0. We should reset the count as well. So it should start from 0. So it doesn't matter either way. It depends on the size of the count. The CNT variable here is 32 bits. So it has to be a 32-bit, 32 prime B0 or 32, D0 probably. B0 you have to write like 32 zeros, right? Just D0 probably is better. Okay. For else if count equals something, which is a maximum, okay, then what's happening here is I'm shifting the LEDs to the left. How could you tell it's shifting to the left? So the LEDs work here, right? So assuming that you reset it at the very beginning, Okay, so you have 0, 0, 0, 1. Yeah, so you are moving 220, which is these 3 bits, to the left, and then you are moving the MSB to the right. And you are doing concatenation. And eventually you are combining all the 4 bits as one 4-bit binary number and assign it back to LED. So eventually what shows on the LED is like a rolling LED, running LED going to the left. Okay? Else, if it's not reaching the maximum count yet, they just add a 1 to count. Keep adding it. So what's the frequency of adding a 1 to this system? No, what's the frequency of adding that 1 to count in this code? Is it doing it fast or slow? Adding 1 like this one. This line here. What's the frequency of that line is being executed or being updated? I shouldn't say executed because it's hardware, it's not C++. How frequent that one is being updated? No. So it's running, like I said, right? So this is a positive as a rising edge triggered. So whenever clock has a rising edge, it's going to update everything in there, right? And for most of the cases, it's reaching else instead of somewhere on the top. It's always else for most of the cases. It takes so many times, such a long time to reach that COMMAX. Okay? So this one is being executed or being updated every 100 megatimes a second. It's counting really quickly, like adding one, do it really quickly. And when it reaches 100 mega, so it satisfies the first this one and shift it. That takes a second. So that's why you are seeing a running LED taking 1 second to be shifted to the left once, right? Make sense? And then it starts counting again. So the reference being used for the counting is the 100 megahertz clock because it's detecting the rising edge of the clock to add a 1 to count. So you have 100 mega rising edges during 1 second. So you're adding like almost 100 megatimes a second, right? So that's how that works. That's a running LED. And then you are getting into the 7-second display. So it's basically using switches to put a number in there. And for example, if I turn on the rightmost switch, it should show a 1 here. And you can see I didn't disable any of the units. So all of them are enabled, so they're showing the same number. We'll talk about that in the morning, right? So they share the same digital lines, the data lines. Here is a decoder. You should be very familiar with that right now. And here's a figure as a reference for you guys. You can see which is A, which is G, which is F, which is E. So if you want to display a 1, you need, it can show on the right side or left side, doesn't matter, it's just a bar, just 2 LEDs. Okay. Let's take a look at the first one again. So it's the same thing, right? So 0, if you got a 0, it enters the first entry as a G2A, definitely G2A. G is here, A is here, no problem. Okay, easy. All right, so the task for this week is pretty straightforward, but next week will be a little bit challenging. So this week, complete the section 1, which are the computer logic, the 2-bit full adders, and the multiplexer, and all these kind of things. show the code, explanation, and demonstrate in the embedded video. Section 2, I think the running LED, and task 3 is very similar to section 2, but you are running the LEDs on 16 LEDs instead of 4. Okay, and task 4 is similar to section 2 as well, but changing the frequency of the running LEDs to ½ second instead of 1 second. Very simple modification to it. And task 5 is section 3, which is just repeating. Okay, it's not, you are not changing anything. You are not showing different letters or numbers on it. But starting from next week, we are going to show different letters. So section 4 is over here, just one sentence. Modify the code, disable any 3 of the 7 displays, and then only show the number on 1 of displays. And also show FLC on 3 of the display units, and then roll it. So which means the FLC, the 3 letters are rolling to the left. You know what I mean? So whenever it disappears on the left, it should show up on the right. So you need the 2 counters. Because when you show different letters on the 4 units, what's happening is you are scanning these really quickly. You are enabling and disabling each unit really quickly by modifying AN, right? And when you are doing that really quickly, so you see FLC here, okay? What you are thinking is static, but actually it's already being scanned for like 1,000 times by the 100 megahertz clock. Then you want to shift it to the left. You just shift your AN, that keyword, to enable the other 3 instead of this one, but still the same data. It's just still FLC, right? But shifted. So there will be 2 counters. We'll talk about that next week, okay? It's something new compared to last year. It should be very straightforward. I did it. I was trying to look for this code. That was from 2018. Well, time flies, already 6 years ago. All right. Heavy load alert for this week. Okay, you have 10 tasks from the tutorial in the lecture and 5 tasks in the lab for this week. Feel free to ask any question you may have. And so Tuesday, I think, will be mostly just a practice, okay? So you guys are coming here, and I think I already covered everything I have to cover for the lecture, and you should be ready to get everything done. So on Tuesday will be a practice class here, okay? So more uncommon, but there won't be a lecture since I already covered everything. So just be there in 570, I'll be there as well. You can work on your tasks. If you have any questions, you can ask me, I'll be there. We'll have a quiz. We'll do a quiz on Tuesday. So we'll do a quiz first, and then you start working on your tasks for Thursday. Yeah, I know 80% of the tasks will be done on Tuesday and Wednesday next week. I know how that works. That's usually how I did when I was in college. The last day and start, no, you guys are better than me, so you start working on that today. Make sure you complete everything. Everything's available on the website, and you can also get help from other people's code from a few years ago. I have new tasks this semester, so it's okay. You look at other people's code, but if you don't have to, don't look at it. Try to code it by yourself. Okay? You are getting help from a lot of different places. Should be done on time. Okay? All right, that's it.